Hello everybody and welcome. This is Daniel Alessandri. I work for the Paul Power Generation Group, and it's my pleasure to welcome everybody here to this webinar. We'll be talking about condensate filtration and how it impacts the operation of steam boilers and steam power plant in general, and more specifically what happens during startup of the power plants. So briefly, this is what we'll cover today. Short introduction on why condensate is such an important fluid in the plant, and then we'll move on to really the core of this presentation, which is discussing contamination issue, especially, of course, what it is and what we mean by it, but where it happens and why. We'll have a tiny bit on chemistry, especially how it relates to this concept of solid contamination floating in the systems. And we'll see what the impact on operations is in steady state, but with a special look at what happens during startup phases. And then we'll move on to really the technology solutions that we can hope to implement and look at to make things better. I'll give you an update on what is happening in our side of the world. We'll conclude and have time for some Q&A. To this effect, you can ask questions using the Q&A box on the left of the slides, and you can obviously ask questions throughout the presentation using this box, but we'll answer them once the presentation itself is concluded. We may not have time to answer all of them today, but they will be logged, and along with this presentation, they will be available for on-demand viewing once this webinar is over. So for a little bit of perspective, this is a very simplistic sketch of a typical steam power plant, and actually in this case we even show in combined cycle mode with the gas turbine sketch you see at the bottom right. And it just basically outlines in green type the various points where water is important for the plant. And today, obviously, we'll concentrate on the condensate treatment and its return as boiler feed water into the boiler system. And really, this presentation is going to be around protecting the key assets of a plant, and in this case, we speak, of course, of the boiler and the turbines mostly. So we'll discuss a little bit of corrosion, deposit, things like tube failure, and even how we manage water, and we can hope to reduce water waste when we speak of boiler contamination-related issues. And then we'll touch, of course, a little bit on the turbine itself and how contamination coming through the steam can affect operations of the turbine itself and potentially reduce output of the plant. So if we dive a little more into the condensate water, a few things to put in perspective right away. We'll see that it impacts both assets and how we hope to protect them, but it also impacts processes and the operation. So on the asset side, we'll concentrate on boiler reliability and operation as well as the turbine, as I mentioned earlier. In terms of processes, really, we'll talk about the feed water, obviously, which is made up about 95% by condensate itself. We'll discuss boiler blowdown frequency and how this is affected by the quality of the feed water, how we manage deep bed resins we may have as demineralization solution for this flow. And then we'll move on to more specifics about what happens during outage, and especially how we come out of an outage and how we start up the plant. And we'll see the very specific issues that we'll face during those critical phases in the power plant. So a little bit more of a visual cue, if you will, on this slide. You see the typical steam cycle we just discussed, so water coming out of the turbine through the condenser, and then all the things that you have to do before this water goes back in the form of feed water into the boiler. And I want to just get your attention on the two circles on this slide, because that's really the location of the treatment, or what we call condensate polishing, is going to happen. And that's usually a combination of filtration, which you see represented in that blue ellipse there, as well as demineralization, usually in the form of large resin bed, often cationic beds that are there to remove ions. So the combination of the two is what we mean by condensate polishing. Now, of course, depending on the nature of the plant and the pressure of the boiler and overall the operation and cyclic conditions of the plant, you may find one or the other. In some cases, this is empty space and you have nothing. So basically water is redirected without too much a treatment all the way to the boiler. Obviously, as the plants become more critical, larger, when the pressure goes up, it's extremely rare to just not do anything for the feed water. But we'll see how the two can combine, this filtration and demineralization, and how the two can play upon each other's strength, if you will, to really get to the results we're looking for. Usually the system is located right downstream of the main condensate pump, and there are a few reasons for it. One of the main one is that where the temperature is very manageable. You know, when we start heating this feed water, everything related to the filtration and sometimes even the demineralization of the water becomes a little more complicated. So the typical condensate polisher will be found directly downstream of this main condensate pump. So now that we've set the stage, we'll concentrate and dive deeper on the issues of contamination, and especially the challenges and consequences it will have on the boiler and turbine operation. So in terms of challenges, really in its most general sense, boiler feed water, of course, is the combination of condensate and makeup. And about 90 to 95% of the feed water actually is being recirculated, the rest being made up with water coming from outside the plant in order to replenish whatever losses we've had in the circuit. Because this water is going back to the boiler, the first thing is, of course, it must be extremely pure. Now, that's a general term. We'll see what that means in a couple of slides. But overall, the strategy is to avoid deposition of contaminants on the system's hardware. This will happen in a few places, but really condenser is a big place for this, but in our case, the boiler tubes themselves is where some of that deposition could happen. Second challenge for boiler feed water or condensate is that we're dealing with high or sometimes very high flow rates, anywhere from a few hundreds to a few thousand cubic meters per hour for some of the largest plants. And in that water, the main specification in terms of solid contamination is that you should not have any. So there is really no allowable amount of particles in the condensate. And actually we'll see that most of the specifications deal with ionic contamination, or at least levels that would indicate that the contamination we would, quote unquote, accept in the system is in dissolved form. So right off the bat, what's the spec for cleanliness in terms of suspended solids? 0. Now, to illustrate this point, here you see a very basic table taken from a very well-known water treatment company's handbook. And it shows you that depending on the drum pressure, in this case we're looking at drum boilers, depending on the pressures, well, you're going to be looking at more stringent contamination specification. And what we're tracking typically, the big contaminants, are iron, overwhelmingly iron, but you can also find copper. And then you'll have things that could come in from a variety of sources in terms of silica, even hardness, and we'll also measure alkalinity. So as you can see, as you go down this table, the specifications become more and more stringent, but overall you can see that we're looking really in the ppb range. And in the lower part of the table is where you find the most challenging applications for boilers that exceed, let's say, the 60 bar or about 1,000 psi. These are some of the most critical plants. Even in terms of drum boilers, they are fairly high pressures. We'll see later how they compare to what we call once-through boilers, and how that presents its own challenge. So as an additional illustration of what we just saw, you can see here typical specification from EPRI, the Electric Power Research Institute, as well as how it's translated, in this case, into a very large European fossil plant. Actually, this is probably the largest European fossil plant. And you can see how some of the specifications may depart a little bit from EPRI's recommendation, but not by much. And overall, we're still very much in the PPB range. A few things we need to remember then. There is no allowable amount of solid contamination in boiler feed water. So the spec for TSS should be 0, no particles. That's where the work really starts. And if it's not the case, one of the problems will be with the chemical treatment. So we'll discuss a little bit of chemistry a little later in this presentation. But overall, the philosophy is the following. Until you've removed solids from the water, your chemical treatment that is designed to control basically the corrosive environment of the system will not work. It will be less cost effective. It will cost more in chemicals. It will be harder to monitor, harder to stabilize, because really this bulk solid contamination in the system, if it exists and is allowed to remain, will kind of throw everything out of whack in terms of how the chemistry of the water works. And the last point to remember is that the resin beds that may be present in the condensate loop are not there to stop particles. So they're not filters, and they should not be used as filters. So let's spend a little time trying to relate this issue of particle contamination with the various chemistry protocols that power plants usually engage in to maintain the quality of their feed water. So why control water chemistry in our system? Well, fundamentally, water in a power plant keeps on boiling and condensing and being transported. So I often say that a power plant is basically, or steam power plant, is basically a water treatment plant, where water is your precious, most important, most influential fluid. And all you do is basically process this fluid around, electricity being basically the byproduct of something that comes out of the generator at the other end. Probably oversimplifying, obviously, but it's very important we understand that water quality and steam really drives how efficiently you can produce power. So because steam and water go through the phase changes all the time, you tend to dissolve or you tend to lose some volatile chemicals, but also some metallic compounds, things like iron, obviously, but also copper. And then you'll find other types of contaminants that, depending on the pressures of the boiler, depending on the temperature, depending on all this thermodynamics happening in the system, will play it out on the boiler tube, on the turbine blades. So what drives this phenomenon of deposition and redissolving is really pressures and temperatures of the boiler. But overall, we are dealing with a perfect corrosion environment. You know, what do we have? We have water, we have metallics, and we have temperature. And this basically is the perfect recipe, so that if you don't control the chemistry and the corrosive, potentially corrosive environment in the system, you will lose control of it very fast before you have a chance to really react to it. So in short, chemistry control is the method that we'll use to fight corrosion in the steam supply system. All the components in it, the piping, the boilers, steam lines, turbine blades, etc., really are influenced by how well we control the chemistry of feed water. By controlling particulates and dissolved chemicals, especially oxygen, iron, copper, and all the other contaminants you see listed here, just a few of them, we'll be able to avoid the consequences of these contaminants on the system, which really boils down to creating a very corrosive environment and attacking the hardware, so the piping and the tubing inside the boiler, but also the turbine blades themselves. Much of the plant chemistry control is achieved by adding chemicals. So here you have a few examples, hydrazine being a typical all-volatile treatment solution, all the way to phosphate, which is probably the most common method to control the environment and the feed water. So maybe just a reminder, very short, on the few chemical strategies or really the range of chemical possibilities we have. EPRI recommends 3 strategies. So all volatile strategy, phosphate chemical additions, which is the most common, as well as oxygenated treatment. So in another webinar, we go over all 3 of them for almost half an hour each, and we go through all the details, but this is not the point of this presentation here. But let's remember overall that strict chemistry control is really recommended by EPRI to optimize plant availability and reliability, especially for supercritical boilers. The other thing to remember, and we'll start to concentrate on that point a lot more, is that the recommended chemistry protocols all require, or actually they assume, that you start with clean water, which is free of particles. 0 TSS being the specification on this side. Okay, so now we'll get to the meat of things and kind of focus straight into our issue of what happens if you do have particle contamination in the condensate. So first things first, what's in our water? And you can see on the slide here 3 different charts that we've taken from actual analysis of power plant contamination in the 3 major types that we deal with. So you got the supercritical plant on the top left, nuclear plant on the top right, and in the middle, your typical drum boiler plant. Now, all of these show that the particles that we see floating into our water are mostly in the 1 to 15 micron range. Pay attention to the units. It says mm, and it's a typo. It should really say micrometer. Right now it shows millimeter, which would be huge. No, we're really talking about microns here. So most of the contamination we see floating in the feed water, or in the condensate in this case, is really small. So it's below 15 micron. And let's remember that number, because when we start talking about possibilities of treatment and how do we get the situation better, it's an important number to remember. So again, what we have in the condensate is actually mostly particles. Over 90% of all metal contamination in the condensate water is in the form of particles. And as we've seen, these are small, but what we know when we actually look at what they are, over 95% of these particles are actually iron particles. And they are in the 3 to 15 micron range, as we've seen earlier, which means 2 things. One, they're easily entrained. They're small, they move, they will get carried all throughout the steam cycle, definitely in the liquid phase, but for some of them, the smallest ones, they can find their way being entrained with the steam itself. And they're not easily controlled. So when you try to remove such small particles in large amounts from such a big flow of water, you got yourself a challenge. As I mentioned before briefly, solid contaminants form a tremendous reservoir of potentially dissolved contaminants. So you're in a situation where as you're removing ions, let's say with your demon beds, what you have floating behind it is this huge amount of solids that basically are going to redissolve in the water in order to maintain the equilibrium, and you kind of are back to square one in that type of ionic treatment. So controlling dissolved matter without a specific solution to address this huge amount of solid contaminants is usually very inexpensive and quite inefficient. And when temperature plays a part in either the outages or during startup, these solids can tend to redissolve in the condensate water, and it's better to catch them cold. Most metallic transports, so these recirculation of this huge amount of iron particles, happens mostly during ramp-up or startup of a power plant. And I'll give you a couple of pointers as to the numbers and the type of crud burst that you could see in such a phase. So if we don't do a good job controlling this contamination away from the feed water, major consequences are going to affect both the boilers and the turbines. On the boiler side, really deposits is what's going to be one of our major issues. And deposits in the actual boiler tubes on the water side, all the way to tube failures from corrosion. But we'll also see that the presence of these solid contaminants increase the frequency of chemical cleans. They will affect the thermal exchange characteristics through the tubes. And we'll see that they can also increase the rate at which you have to blow down the drum. And this loss of energy can be up to 3%. So big consequences on the boiler, but also on the turbines themselves. Contaminants that are entrained with the steam end up in the various stages of the turbine blades. Things like copper and silica deposits are known to force a loss of efficiency and sometimes power downgrade on the turbines. It also forces you to clean more often with more aggressive chemicals and a larger quantity of it. So both on the boiler side and the turbine side, solid contamination, these particles floating in the system, will have a tremendous impact on the operation and the efficiency of our system. As a quick example of one of those well-known phenomena, I'll just want to show you a slide talking about what we call under-deposit corrosion, which is the corrosion of the tube surface under an iron deposits on the tube. So the sequence is well known and fairly obvious. You start by depositing iron because iron comes out onto the side of the tube as the water boils away. What ends up happening is this coat of very porous material sticks to the tube and creates tremendously hot spot, behind which water can seep through and flash off and release tremendous amount of corrosive materials, acids or base. And these are the corrosive components that will eat away at the tube itself behind the deposits of iron. You see on the right the picture of what a tremendously contaminated tube can look like from the inside, and it's all red, it's all rust, and it's all deposited on the side of the tube. And other than the mechanical failures of the tubes themselves, even before that happens, any deposit of scale on the tube will dramatically decrease the heat transfer through the tube. So what ends up happening is you have to burn up more fuel in order to bring the water in the same state that you would if you had a clean tube. Here on the curve, you see some of the numbers and the quantification of this phenomenon. As you increase the thickness of the scale on the inside of the tube, your heat transfer can be reduced all the way, in the extreme cases, to 50%. Now, of course, usually your entire tube is not contaminated the same way. But it's undeniable that as you build up scale in the tube, you'll see the efficiency of the heat exchange go dramatically down. And contamination will also impact turbine efficiency. Copper and silica especially that are present in the condensate can go all the way to the turbine and deposit on the blades. In the high pressure stage of the steam turbine, if you have deposits, either copper or silica or other contaminants, you basically end up forcing vibration and therefore lower output or forced derating of the machine in order to avoid mechanical wear to be excessive. Copper is a special challenge in water because it's quite hard to measure and control. Its solubility range is right in the range of pH, temperature, and pressure that we're dealing with usually, so that copper tends to go in and out of solution. Sometimes it's particles that you could hope to be removing. Sometimes it's dissolved back in the water and all the way making its way through the turbine. So it's a specific challenge. Silica in the same way is a specific challenge for other reasons. It usually comes from the outside. Very few components internally have silica in them. So it's usually a sign of either makeup water coming in that's not up to par or some leaks in things like the condenser tubes, for example. And silica also will take place in many forms, or be found in many forms in the system, both dissolved and colloidal forms. So I want to spend a little time discussing blowdown. So blowdown, to be very short and precise at the same time, only happens in drum boiler plants because what you blow down is the drum itself. So first thing to remember, supercritical boiler that you see the symbol on the right side, that's not a candidate for blowdown. So blowdown really is forcing the contamination to leave the drum boiler basically by opening a giant valve. And you evacuate the water and you hope that most of the contamination leave with it. It's usually influenced by the cycle of concentration in the drum. So the faster contaminants accumulate, the faster contaminants concentrate in the tube, the more often you will have to open that valve and blow down. So as you can imagine, blowing down is huge waste of energy. And you have to do it because you hope to keep the system clean. But in doing so, you basically throw out this hot water that you spent money heating by using fuel, and then you basically throw it out, and you can hope to recycle it and clean it and bring it back to the system. Nevertheless, it's kind of wasteful. On the other hand, it does evacuate the bulk of solids contaminants. But I want to bring your attention to this quote by EPRI themselves. And I'll read it just straight through. Blowdown is not effective for corrosion product buildup control. Even if continuous blowdown is employed, buildup rate would not be significantly affected. And this puts more emphasis on the need to minimize the introduction of corrosion products with the feed water. Long story short, better to catch contamination before it gets to the boiler rather than try to have this solution where you're basically throwing the baby with the bathwater, if you will, or the water along with the contamination in our case. So, by looking at the system in general, by briefly touching on chemistry, by qualifying, really what we know is floating around our system, we've set the stage to discuss really the specific case of startup. How is it different? What happens? And the specific challenges that we are going to face during the startup phases of the plant. So the basics first. During startup, the plant needs to reach a very high quality of feed water before the turbine is allowed to be put online. So what that means is, until you've reached the specification that you set for yourself in the water, you're not going to start the plant. So these startup phases can last up to a few days, and of course, the longer they take, the more money the plant is not making, just due to lost production. During startup, very importantly, a great amount of contamination is transported through the system. We haven't talked about the metallurgy of the system itself, but basically most of the chemical protocols I mentioned earlier, volatile, phosphate, oxygenated, are related to making a protective layer, so a passivation of the internals. Magnetites, hematites in various ratios will be coating the inside of the tube, and that's really how we fight corrosion. Now the problem, during startup, these protective layers of magnetite, in my case here, can be compromised, and therefore large quantity of particles will be released, and that's what we call the crud burst or crud release. That is why high efficiency filtration is critical to a proper startup, because you want to avoid the consequences of this magnetite layer just basically dumping into the water and starting to be carried through the system. And we know it happens because contamination during startup can be 100 times that of a continuous operation. So that in this example, for a plant with a typical annual outage, so big baseload plant, during 3 days of startup, the water will transport as much metallic contamination as it did throughout the entire year of continuous operation. So to visualize what I mean, this is a picture of a typical condensate loop, and you can see clearly the contamination that is present in the water. Metal oxides, that's how we recognize these dark-looking particles, oxidized metal. Our goal is very simple. The water should be free of particles. So the picture on the right is our objective. And the typical technology that will take us from one to the other is a good condensate filter. And here we come to really the startup issue and the core of our problem. This is a little chart that shows the amount of particles present in water during a startup phase of a very large steam power plant. And you can see that the black bars are extremely variable, whereas the time frame itself is quite short. We're talking about a couple of days total represented on this chart. So that you can see that overall the contamination is very unstable. So what I show in the red circle is this peak of contamination all the way to almost 40,000 particles per milliliter in the water that are released violently in the system, and that's what we would call a crud burst. These conditions during startup are very transient, and therefore one key aspect of it is how difficult it is to measure. So because we were doing a study and analysis, we were really on top of it, but if you only take, let's say, particle samples every 3-4 hours, which is already very high frequency, then you may very well have missed this huge peak of contaminants. What really compounds the problem is contamination is often underestimated because it's hard to measure, but also because it will eventually disappear from the water. Efficient startup filtration is a critical aspect to maintaining this healthy boiler during normal operation. So the job you do on startup protects the boiler throughout the year. And I want to come back to this idea of contamination being, disappearing in the system. And to that effect, I will just read the quote here from a conference, a utility chemistry workshop conference, that says, "Suspended solids will deposit in areas of high heat and flux." So let's face it, we're talking about boilers here. "What has appeared to be a rapid cleanup of suspended solid as the boiler comes to full power is the deposition of those solids in critical areas of the boiler. And that's key. What it says is, yes, your water will be clean. Your water will get clean. But the reason it will get clean is because all the nasty things that are in the water are actually now on the side of your boiler tubes, on the side of your piping, and on the sides or the surface of your turbine blades. So really, many times I've had conversation where people can show me a curve of particle contamination going down as they bring up the plant to full power. And you can't deny that. The problem is, where is this contamination going? Because it's certainly not disappearing. So either you remove it with mechanical ways, like a filter in our case, or something else is picking those up. And that something else is very often the boiler. And that's where a lot of the problems will start. Okay, so now I want to move on to potential solutions. So let's spend a little time talking about technology for condensate polishing. So in general, making clean feed water is really about using a combination of demineralizers and filters. And each has their role, so that on the demineralizing side, so the term demon beds is what we refer to. The demon beds are there to remove ions, so dissolved contaminants. They usually are used inside large vessels with regenerable resins. So when the resin is spent because it's been capturing those ions, then you have a chance to regenerate it by basically flowing strong acids or strong bases through it, depending on the type of resin you're using. In any case, it is a very poor filter. So usually you'll find 30 to 50 micron particles in the vessel itself that have been caught. But think of it. This is at the expense of resin life. The fact that we find solids in a resin bed is not a good thing, because that thing should not be used as a filter. To use a filter when it's better to use a filter. So two types, regenerable, which we also call backwash systems, and disposable, which are the form of filter cartridges that you basically throw out when they're full of contaminants. So the two main concepts for condensate filtration are disposable and backwash, as I just mentioned. So let's start with what we mean by disposable filters. They are designed to control particles down to a few micron, but they are not designed to remove dissolved salts and dissolved metals. So they cannot do the job that the resin beds do. However, they tend to have small footprint, and we'll get to compare that with the other filter technology, the backwash regenerable systems. But they are usually very easy to use, and they have some of the lower costs to implement and install. Overall, it's simple. It can be very efficient, and it's small and usually cheaper to install and buy than their backwash counterpart. But you do need to change filters. So you end up with solid waste, right? The filter material, plastic usually, or polypropylene is very standard, plus whatever contamination is captured in it. Now, of course, this contamination is very rarely either nasty, hazardous, or dangerous, right? Usually made of rust particles. You can see here a few pictures of actual power plant installations, and when you realize that a lot of these are full flow condensate systems on plant running anywhere between 300 to 550 megawatts for those on the slide here, you realize how nimble and small such a system can be. And on the other side of the spectrum, we have what we call backwash filters. Now, these are designed to self-clean, so they're regenerable filters that typically will stay in place anywhere from 3 to 5 years, and would regularly clean themselves, if you will. They are designed to control particles. They are filters first and foremost. The big difference with the backwash filters is they could be designed to control dissolved contaminants, so act as an ion exchange system. By simply adding an exchange resin to the system, it comes in the form of a powder that gets coated on the side of the element and act as a demineralizing system, so that your single cartridge becomes at the same time a filter and a demineralizer. Now, this combine or total control is then possible in one step. The large flows is what determines usually the use of those backwash systems. However, typically it's a very large footprint. It's quite expensive to buy, to install. It's heavy capital equipment. You can see the size of them on the pictures. They do generate liquid waste because that powder plus the particles, when they get expelled from the filter during the regeneration, well, that is waste that needs to be handled. So overall, very efficient systems can get great results at the expense of usability and maintenance that is typically heavier than what you would find or require from a disposable filter system. Now, what's interesting to know is that technology evolution tends to favor the use of disposable filters. Innovation and progress in filter technology allows much larger fluxes to be treated without sacrificing efficiency. So your micron rating, whether you're looking at 3 or 10 micron for these systems, can be achieved in much larger flow rates than in the past. The main consequence being that the need for backwash systems is decreasing because larger and larger flow rates can be processed with disposable filters. Direct consequence is a reduction in capital cost investment to install these systems, a much better usability, user-friendliness, simplicity of the designs, and at the same time, very high consistency in the results linked to the simplicity of the system and really the straightforward method by which we eliminate all the subsystems that are typically necessary for a proper backwash to operate. To illustrate the difference, you have here 2 pictures that were taken from the exact same power plant and actually an upgrade going from an older backwash system that needed 403 elements to process the water. And that was basically taken away and replaced by a much smaller filter system using only 34 elements. Now, these are disposable filter elements compared to backwashable, so they do need to be changed, and typical change out could be 6 months, every 6 months, a change out of those filters, or every year in the case of really a baseload plant where we don't see a lot of these startup shutdown situation that we know contribute large amounts of contamination. Just one last note, look at the color of the elements on the left pictures. Obviously, who is to deny the fact that iron particles, rust, are really the challenging contaminants in this system? I mean, they're coating everything inside the system. So again, iron, about 95% of our problem in these systems. So in terms of operational advantage, other than small size and lower capital cost, we have here some of the main points in terms of flexibility especially. So these type of disposable system, which you see the picture at the bottom left, can be used either as startup-only filters or full flow. They can be installed in simplex or duplex configuration. The micron ratings adjustments can be done on the fly. That is a direct result of the ability to basically open up the vessel very easily and in about an hour change 30 elements and replace them with either the exact same or a different micron rating. We've had instances where These filters can be used with a very fine filter during startup and coarser during regular operation, where we expect the contamination to be a lot more stable and the water to be a lot cleaner, for example. And you can see on the right side what it takes to change elements in a large backwash system. Somebody is actually inside the vessel changing hundreds of elements, as opposed to only having to pull these horizontal elements from the outside. So this next slide kind of outlines the main benefits we expect from this type of better filtration. Obviously, the ability to start the plant faster by cleaning the water a lot faster and reaching our lower limits a lot faster. The increasing availability of the plant, because it's all about protecting the boiler systems against corrosion, as we've seen earlier, and therefore reducing things like unplanned outage that could come from boiler tube failures. It's also used as a way to reduce the rate of drum blowdown, and therefore saving water, reducing waste, or even eliminating blowdown altogether. But because we are placed upstream of the main resin beds, if they are present, you get to increase resin life. You get to maintain your megawatt output from the turbine if you protect the blades against carryover of contaminants, especially copper or silica, and you reduce the deposition of these contaminants onto the blades. And of course, we reduce the solid waste by going to a disposable filter that would last for a long time. So long element life, as well as the low number of elements that are needed to do the job, will reduce solid waste. So all these benefits obviously have to be quantified, and they are tangible benefits. Other than this flexibility and the small footprint, which are basically the hallmark of these small, nimble, disposable filters, we get to have very measurable effects on the system. You get to reduce total contamination of copper and iron by over 80% based on total concentration. If we only looked at solids, we would have an efficiency above 95% for particles. So basically almost all particles are removed before they have a chance to get to the boiler. You get to reduce, therefore, your chemistry hold due to iron or copper by over 50%. That is how we start the plant twice as fast. But because we are placed in front of the resin beds, we tend to protect those as well, and you get to see an increase in the life of the resin, and your frequency of regeneration of the resins drops by at least 30%. And very importantly, you get to really protect your boiler tube against deposits and under deposit corrosion failures. And that reduction is conservatively at 80%. In truth, the examples we've seen from the field is that we tend to eliminate all cases of boiler tube failure due to under deposit corrosion, which is really an extreme failure of that system. And finally, as I mentioned, you get to reduce blowdown. Because you clean the water, you lower the cycle of concentration, and you tend to reduce blowdown at least by 50%. So the quantity of water that you currently are dropping in the boiler blowdown, basically cut that in half. Again, conservative number. So what have we learned from what we just saw? Startup time can be dramatically reduced by using good filters and controlling metal transport in the transient phases. Catching solids before they get downstream will save on boiler tubes, on resin beds. It will protect turbine blades, and it will reduce water costs through blowdown reduction. And in terms of technology, what used to be very difficult to do with disposable filters, and therefore we had to use large, expensive backwash, is now getting to be a lot more affordable, a lot more possible, and that's all about the filter technology. That allows our system to be smaller, easier, as or even more efficient in some cases, but very importantly, it becomes a very flexible solution. And it becomes a very cost-effective solution. So in a sense, it does not have to be either or anymore. In the old days, you'd have to make a tough choice between spending an ungodly amount of money on a very large backwash system or find another solution that usually meant all these benefits were not possible for you. So contamination was allowed to go through. The only proper treatment was just with the resin beds, and you needed to regenerate those too often. So this is done. You don't have to sacrifice protection in order to make the plant more user-friendly or more easier to operate. So that's the main gain from using new high-flow disposable filters in our systems. So on this note, I'd like to thank everybody for your attention today. It was my pleasure to discuss this. I'm now going to reopen the line, and we'll get to go through a couple of the questions that we've received during this call. All right. So first of all, again, thank you. I got a couple of questions for us during the call, so I'm just going to go two of them, and then we'll have to close. Of course, you can always reach me by email. You saw my address on the last slide. And, of course, this whole webinar will be available on demand, so there'll be other opportunities to ask for the question, if you will, and don't hesitate to do so. So I got a question from Fred here. Is the same type of filter applicable in combined cycle plants? And it's true that what I covered today, I mean, I mentioned combined cycle in the very beginning. But yes, the answer is yes. And actually, if we look at the past few years, about half the projects that we've been involved with were on the HRSG of combined cycle plants. So some of the issues are different. Contamination can take different form, and especially how it impacts various stages in the boiler may be different, but in terms of the need and the capacity to capture solid particles, the issues are basically the same. And these flexible systems are even more, I would say, adequate for combined cycle plants. So that's definitely a yes to your question, Fred. And then Mike was asking, what's the maximum flow rate you can use with disposable filtration? That's an interesting question, and I would say the limit is in the cost and the size. So once you go to very, very large flows, and I'm, multi-thousands of cubic meters per hour, that's where the benefits you would expect from a nimble, small, easy-to-use system kind of depart a little bit. But you got to remember, we have systems that use disposable technology up to 34, sometimes 40 elements, which is about the equivalent of being able to push between 800 and 1,000 cubic meters per hour through one single vessel. That's that type of ratio. Much above that, you have the choice of multiplying the vessels, obviously. So I would say, in theory, to be clear, there's no upward limit other than what you're willing to first, obviously, to pay, but you're willing to work with in terms of large system. So I hope this was interesting for all of you. Definitely, I had a good time. Again, this will be available on demand. You should all receive a notice very soon when the webinar is available for you to watch anytime, and certainly I encourage you to do so. And once again, I encourage you to contact me later if you have questions that pop up. So on this note, again, thank you very much, everybody. It's been a pleasure. I wish everybody a great day, a great evening for those of you based in Europe, and we'll be talking soon, and I hope to see you soon in our next webinar. Thank you, and goodbye.